was trying to understand what the conference is about, and the conference seems to be about the International Seminar on Automorphic Forms. So I decided to speak about a talk that happened in that seminar by my collaborator Naomi Sweeting. And I guess, so there's some overlap with what I'll say and what she said in the seminar, but hopefully it will be different enough that it won't be boring. So I want to talk about the arithmetic of Fourier coefficients on the exceptional group G2. And we've seen in this conference many beautiful properties of Fourier coefficients. For example, holomorphic modular forms, also mass forms, and also modular forms on other groups like pseudo-modular forms or Hilbert modular forms. And I want to try to convince you that G2 also has a nice view of Fourier coefficients that are interested for arithmetic purposes. So I want to start with an example that might be familiar to you of what the arithmetic of Fourier coefficients may look like. So I want to start with the work of Shimura from, I think, 73, who associated to a weight 2k modular form, or maybe it was the other way, but okay, a weight k plus 1/2 modular form via converse theorem. And so this one is a half integral weight, but it's a holomorphic modular form. Okay. And then Walsh-Berger in the 80s, so in the 80s, so I guess the first thing he did is kind of restated Shimura's construction in terms of a theta lift from SO21 to MP2, the metaplectic group, and also proved this very nice formula for the Fourier coefficients of the lift. So what he proved is that if you look at the Fourier coefficient, if you look at the Fourier coefficient AD of the modular form of the lift, then it will be up to some constant, more or less explicit, the L value of the modular form, twisted by the character associated to this D. So D is going to be some square free number. And this character, and this is the central L value. This character here, one way you can think about it is that you can look at the induction from Q to Q squared minus D of the trivial representation, and that will have a copy of the trivial representation, and the other thing will be this character. Okay. And it's the square of the Fourier. Okay. So this is a classical result of Walsh-Berger, and it has a very nice application due to tunnel from 83. I'm not sure anymore. To the congruent number problem. So it gives this sort of partial resolution to the congruent number. So it turns out kind of these L values for a specific choice of f have something to do with what are called congruent numbers, and understand this relationship to the Fourier coefficients lets you then explicitly compute this form and say something about the problems. So this is some classical story. So this is one example I wanted to mention of what Fourier coefficients of modular forms can tell you about arithmetic in the classical sense. So the question that I want to ask today is, what about groups G, so reductive groups that don't have the analog of holomorphic modular forms, so that don't have what are called holomorphic discrete series. So the examples, like I said, Hilbert modular forms or Siegel modular forms, things kind of generalize because, so one way, this is just maybe an aside, but one thing you can think about is the symmetric space associated to G. And what I mean by this is that this has no Hermitian structure. So for example, there's no Shimura variety and so on. Okay, and so the example that I'll study is the group G equals G2. So not only does it not have holomorphic discrete series, it's also one of these exceptional groups. Okay, and maybe you're not used to working with such groups, which is okay. I drew the root system here. Okay, I don't know how much that tells you or not about what the group looks like. I don't really need you to know much about the group. I'll tell you what I need you to know about it as I go. But it's one of the exceptional groups, so it doesn't fit into these infinite systems like symplectic groups or orthogonal groups, and it behaves a little bit differently. Okay, so my goal for today is to talk about some results that are similar to those results for classical modular forms, but for the group G2. Okay, and my plan is to immediately jump into some statements about G2 and then explain how they work in more detail throughout the talk. So I want to really jump forward to a couple of theorems. So the first theorem, let's call it theorem 1. So this is due to us, and this paper is from last year. Okay, so the first theorem is sort of the analog of Shimura's theorem, or maybe Walsh-Bourget's construction, which gives a class of modular forms in G2. So it produces examples of these modular forms associated with classical modular forms. So we start with a modular F, the modular form F, which is actually the theta lift of a character. So it's a dihedral form. So it's a dihedral form associated with some k over q imaginary quadratic. So it's just a classical sort of theta series. And chi, some Hecke character. And I want to assume that this has trivial Nebentypus, so trivial character. So in other words, the character has to be what is called conjugate symplectic. But okay, so the form has no character, and also I want to assume that the central L value is not equal to 0 of this modular form. Okay, and it's, okay, I'll record the weight, it's 2k. So it's the same kind of modular form here, but I restrict to the case where that form itself is dihedral. Okay.
That form now is a classical, is an elliptic modular form?
Yes, classical modular form. Yeah. It's the same. So this is a modular form. So it's a cuspidal modular form. Okay, so cuspidal with 2k in some level. I don't know. Okay. All right. And then in this setup, what we did is we constructed some modular forms on G2. So let's call them similarly to there, like this curly f associated to maybe chi. And then there's an extra piece of data which I'll call epsilon. Okay, so this is some modular form on G2. And it's labeled by not only like the chi, so not only the form you start with, but basically you get multiple forms over here due to what is called the R-form multiplicity formula. And I'll explain exactly what this collection is in a second, but let me just write it out. So a collection epsilon, which is a collection of signs for all the primes, so these are signs, and they satisfy okay, some properties. So you can construct a bunch of these forms. It depends on some choice, and I'll explain this choice in a little bit. Okay. The takeaway I want to say is that like there's a similar thing to this theorem of Shumo. You can start with a modular form, and instead of going to the metaplectic group, you go to G2. Okay? That's theorem 1. And then theorem 2, I hope this will work, which is by the same set of people. And this is in progress, and it's almost finished, so I hope it will be out in a couple weeks or so. Okay, so this is a formula for the Fourier coefficients for the absolute value squares, relating it to an L value. So I haven't explained what Fourier coefficients look like for these G2 modular forms. So this is what I'll do sort of next, but they're labeled by, so over there what play the role is imaginary quadratic fields. So somehow those Fourier coefficients you can think about as labeled by sort of q squared of minus d, or even like kind of the ring of integers of that is what technically is happening. So here E will be a cubic étal algebra over Q. So it could be something like Q times Q times Q. It could be something like Q times F, where F is quadratic. Or it could be a cubic field extension. All right, so this is a cubic algebra. This is what we'll label the Fourier coefficient. And so the formula looks like this. The Fourier coefficient labeled by E, or its ring of integers, of this modular form that we constructed. So its absolute value squared is equal to the following L value. So it's F twisted by a two-dimensional representation associated to E at 1/2. And it's not just up to an arbitrary constant. We even work out exactly in our normalization. This is delta E. So the discriminant of this étal algebra to the power k minus 1. So here, VE is similar to the character. So you induce from Q to E the trivial representation that splits off a piece of the trivial representation plus a two-dimensional Artin representation VE. So this is two-dimensional. So what we're seeing as Fourier coefficients of certain modular forms on G2, twists of L values of modular forms by now cubic étal algebras. And then if I want to be, okay, so it's equal to this or equal to 0 sometimes. So let me, so there's this, it kind of depends a little bit on those epsilons, and I'll state a more precise theorem in a little bit. So whenever it's non-zero, it looks like this. All right, any questions about sort of the motivation or the statements themselves?
So delta E.
Sorry?
Delta E. Delta
Sorry, I can't.
delta E to the power k minus half.
What is what? This?
Delta
E.
Oh.
discriminant.
This, what is this? The discriminant, yeah. So this is just the discriminant of the cubic field.
Is VE always irreducible?
No, it could be the sum of two characters as well. So sometimes it's the sum of two characters, sometimes it's irreducible, yeah. And it could even, like, if I took E cubed times Q times Q, this could even be like just 1 plus 1, and then it's just the product of the two L values. So. Any other questions? Yeah.
I don't know if you're going to say later, but if this is the theta lift thing you're constructing, which dual pairing are you considering?
Yeah, so it will be constructed as an exceptional theta lift for some exceptional groups. So it's I'll try to explain that as I
We'll
go.
get to that.
Good question, thank you. So it's also like theta lifts will play a role in just a second. Any other questions?
Just a quick question. So were Wahlspeche formulas like this known for other exceptional groups? I mean, the theta lifts, I guess, were constructed.
For which exceptional group? So I don't.
Just some exceptional groups, right?
No, I don't know of.
Okay. So this
I
is
don't
like
know
the
of other
first.
examples. No, but I don't want to say that either because I just don't know. But maybe other people know like other ways in which this formula has been generalized to some groups. I mean, definitely it works for Hilbert modular forms, but I don't know. Like you have to be like in the right setup for such a thing to work, and I don't know exactly of the right setups in general.
Do I vaguely recall that there's a formula relating Fourier coefficients on G2 to toral periods on GL3?
Yeah, so this will play a role
Okay.
in the proof of this. Yeah, in this case it will be on PU3, not GL3, but yeah, it will be of this sort.
Do you have any sense of the sparsity of the Fourier coefficients of F? Like how often do they vanish?
Yeah, so that we know precisely. It's not, or of F, or of the capital F, sorry.
Capital F.
Capital F. Like when is it
As
zero?
E varies, yeah.
Yeah, so this we have worked out
Sometimes.
exactly. It just depends on like, okay, so there's the level, and so at primes dividing the level, you basically have to make your cubic étale algebra compatible with the epsilon p that you've chosen. The epsilon, so the epsilon.
Okay, so you can't vary E too wildly.
So at p, you kind of can't vary e if you fix all the other data, or you can vary it amongst the class of e's. For example, at infinity, so this condition, for example, at infinity means that this cubic étale algebra has to be totally real. So this is the kind of condition you get at infinity, and then you get some conditions at primes. I'll write them down, but if you have your favorite totally real cubic étale algebra, I can arrange for that Fourier coefficient to be non-zero and related to an L value. But like you have to choose these epsilons according to what you want.
The indices that are not square free would be related to the square free ones by like Hecke action, just like in the Shimon case.
So here we don't, so you mean this? Yeah, so there are some Fourier coefficients that are not for maximal cubic étale algebras, and we don't say anything about them.
Okay.
So these Fourier coefficients in general are labeled by, cubic rings, and those, so those cubic rings may or may not be maximal, and then we only say something about the maximal ones. And okay, we could prove something about non-maximal ones, but it's a bit of a mess to try to say. Like again, you would have to choose a different form according to what non-maximal Fourier coefficients you want to see, and it's a bit of a mess. Yeah.
How much is known about non-vanishing of this L value?
These kind of L values, so you can put yourself, for example, in this situation, and then it's twisted by a quadratic character, and so a lot is known about, for example, in this case, you can arrange for things to non-vanish if you vary f. In this case, like for a cubic field, I don't know actually of I don't know of any results that talk about non-vanishing of this in general. Like, can you always find an E or infinitely many E's such that this doesn't vanish? Probably, but I don't know actually. Okay. So let's get on with the actual talk. Okay, this took way longer than I thought. So part one will be quaternionic modular forms. Okay, once I should write this in here. So quaternionic. And Fourier extensions. So I want to explain what the analog of holomorphic discrete series. So what is the analog of holomorphic forms for groups like G2? And the idea is to kind of look at the representation theory at infinity. So Gross and Wallach in some year, which I have to look up. So 96. they wrote down a specific family of representations called, they wrote down sort of a family, pi k, labeled by integers, of kind of small, in some sense, in terms of k types, they're kind of small representations of G of called, so pi k they called a quaternionic discrete series of weight k. Okay, and so these, so these should play the role of holomorphic discrete series for groups that have them. So if you did have a Hermitian structure, kind of the smallest representations are holomorphic discrete series, and those have the nicest arithmetic properties. And this group, for example, G2, doesn't have holomorphic discrete series, but it has these quaternionic parts. So we call a modular form quaternionic if this is what it generates at infinity. So let's write that down. A quaternionic modular form, QMF, on G2 is a holomorphic form such that which generates an automorphic representation pi such that its infinite component is one of these pi k's. And k is called the weight of this modular form. Okay, so you should think about this as the analog of holomorphic modular forms of weight k. So this is kind of the class of modular forms on G2 that we'll want to study. And now we have to talk about their Fourier expansion. So this is due to Gahn, Gross, and Savin. So as you notice throughout this talk, many people working on G2 have names starting with a G. And you may feel bad about Savin, but his first name is Gordon. So it's also part of the party. Okay, you may feel worse about Aaron Pollack, but so what they kind of proved is that these QMFs have a good theory of Fourier expansions. And I want to write down what that looks like. For GL2 Fourier expansions, you have to look at like a parabolic, so the upper triangular matrices, and integrate along the unipotent radical. So I want to show you a nice parabolic on G2 called the Heisenberg parabolic. So P equals n times n will be what is called the Heisenberg parabolic. And I'll show you what it looks like over here. So you can look at these roots over there. And so at the very top, there'll be the center of this parabolic, which will be, of course, isomorphic to GA. So G2, by the way, I'm taking the split group G2, so it's split at every place. Okay. So there's this, and so the whole thing will be the unipotent radical. And the way that works is that these roots down here, they give you kind of the quotient of n times z, which is then GA to the 4, so 4 copies of Q or something. And then kind of the commutator of all these roots is the center up there. So the quotient of n by the commutator is GA to the 4. So here n is actually a Heisenberg group that you may be familiar with if you study the theta representation. So Heisenberg group, so in other words, like let's say n of q is isomorphic to, mod z of q is q to the 4, and z is, this is GA. So q. So this looks like that, and then to kind of the parabolic itself you also add this, which is the levy of the parabolic. And altogether you get something like this, which is P. And so M here, as you can see from there up to the center, but M, the levy, is just going to be GL2. Okay. Anyway, so there's some favorite parabolic that they want to take for the Fourier expansions. And the Fourier coefficients will kind of be labeled by Holmes from n mod z to GA. And of course, this is identified somehow with GA to the 4. So in other words, they'll be labeled by, let's say, like 4 rational numbers, right? So S of Q will be isomorphic to Q to the 4. So then what you do is you have to pick sort of, so if you remember from these talks on mass forms, what Fourier expansions look like, you have to pick some Whittaker functionals and expand using those Whittaker functionals. So here, Pollack wrote down some very explicit generalized Whittaker functionals. So for all E in, let's say, X of Q, there's an explicit function, W, labeled by this curly E, from MR to C. Okay, and then, so such that the following, which you can use to write down the Fourier expansion, so such that for a quaternionic modular form F, the first thing I want to do is kind of integrate out the center of this parabolic. So I'm going to define Fz of G to be the integral, you integrate out the center, Gz dz. Okay, so you get rid of the center, and then the rest is labeled by this quotient. So, okay, for this you define that, and then this has a nice kind of Fourier expansion. So Fz of Ng will be equal to the sum over these E's of X of Q of this Fourier coefficient AE times e to the minus 2 pi I. Okay, and now it's kind of E paired with your N, but so E is already a homomorphism from here to here, so I can even write that it's E evaluated at N, this N, times the Whittaker functional associated to E evaluated at G. So here N is in MR, sorry, N of course is in NR, and G is in NR. Okay.
Sorry, what do you mean by integrating over this bracket set?
Oh yes, the bracket Z is just the adelic quotient. So in general, yeah, this is like some shorthand notation for the adelic quotient by the Adel's way. Thanks for the question. Sorry. Yeah.
The E's here are all of xq or some bounded denominator, like in
So a priori it's like this, and then one can prove some theorems. So for example, if f has level 1, then only the integral ones will appear. In general, other ones may appear, and so on. For our modular form, this will only be non-vanishing for integral things eventually. So yeah, but it's a good question. Yeah. So there is definitely, like, a lot of these should vanish, and it should be some sort of integral ones that are supported. Okay, so I should say, like, before I said that this has something to do with cubic rings, so what does E in X of Q have to do with cubic rings? Sorry, X of Q, which is Q to the 4. So if here I take A, B, C, D, I can define a cubic étale algebra E as the quotient of like Qx by this polynomial ax cubed plus bx squared So at least there is a cubic État algebra over Q, and then OE. There is some sort of OE actually, which is kind of in E is a suburb. Okay, and so there's some precise way in which an element E kind of determines a cubic ring, and I just don't want to get, like, you can read it off from the ABCD, but in general it's not monogenic, so you have to take like two generators satisfying some relations in terms of the ABCD. But I'll be interested in cases where this is actually the ring of integers in a second. Okay. So the question for today is, do these Fourier coefficients over here have some arithmetic significance? And that's what we'll get to. All right. Any questions about this Fourier expansion?
And if A is 0, this looks like not cubic anymore.
Oh yeah, so that's another thing, like the non-degenerate cubic. So so A is not equal to 0 is called non-degenerate, and then, or wait, yeah. So then there'll be some degenerate thing. You could also imagine if like B equals C equals D, then this is not étal, for example, it's ramified. So these would be called like degenerate Fourier coefficients, and okay, they're a priori, but they shouldn't like contribute. But okay, we haven't worked out all of these things. I think we could, but we didn't really focus on that. Right. So the next thing I should give you is examples of quaternionic modular forms for which you could try to compute the Fourier extensions. So examples of Q of X. So when you learn modular forms, the first thing you learn is, the first examples you learn about are Eisenstein series. So let me mention something about Eisenstein series. So there are some Eisenstein series E2k of weight 2k, we're going to call them 4. So they were studied by G2S and also I think Jan and, or maybe it's Jan Rallis. Okay, sorry. Why am I doing this? Jan Rallis. Show. And they have the following property. So if you look at the Fourier coefficient labeled again by E, where E corresponds to some cubic ring, let's just say OE. This is E corresponds to A, which is a cubic ring. Then AE of this E2k is some zeta value. So it's the zeta function for this cubic ring evaluated at 1 minus 2. Okay, so Eisenstein series have something to do with L values as well, but just say of zeta functions of cubic rings. Okay, and then the question was after this, how can you even write down cusp forms? Quaternionic modular forms which are cusp forms. And so the first like proposed construction was due to Gan and Gurevich. I think in 2008 or something. Right? So of course G and G is the prevailing theme. Okay, so their construction, I'll say briefly how it goes. So it starts with PGL2 and our modular form F, and it ends on G2. So producing something like FF. And it goes via, so first what it does is it goes via PGL6, sorry, PGSP6. So symplectic group in sort of over 6, and it uses here a construction of some cap forms on PGSP6 due to Ginsburg, of course, G. And then from here to here, this is really kind of what the bulk of their work is to apply, to go from here to here via starting with representations of Ginsburg. And so this is the first moment in which a theta lift happens. So this is called an exceptional theta lift. And so it comes from the fact that there's a dual reductive pair in PGSP6, PGSP6 times G2 in the exceptional group E7. And so when you're used to working with theta lifts, what you do is you embed a dual reductive pair in maybe some symplectic group. In the symplectic group, there's the Weyer representation. So let me flip these boards. Okay. So normally on this group, there's the Weyer representation. It's usually a symplectic group, and then you restrict it down to a dual reductive pair within it, and you get a correspondence between the representations of the two groups. And here, you also take a representation on E7 and restrict it, and it's called the minimal representation. So it's somehow a representation that's the smallest possible in some way. Because if you took a very big representation, it might not provide a bijection between the irreducible representations, and so the Weyer representation has this property that is quite small. And so people manage to kind of write down abstractly what this means. Okay, so this is a brief rundown of what happens over there. Okay, so the problem now is okay, so there's some way that they found to go from PGL2 to FF. Let's call this FFGG for Gan-Gurevich. But at this point, actually, it's not known. So it's hard to actually prove properties of FF. It's some modular form. And sorry, it's non-vanishing if you assume that the L value doesn't vanish. So this is the crucial assumption also in here, that the L value doesn't vanish to start with. But for example, this modular form is not known to be a quaternionic modular form. In other words, this component at infinity is not actually determined in general. It's only conjecturally expected to be quaternionic. And also the ramified factors are not determined. So it's a construction, but it doesn't prove all of the R for multiplicity formula. So it doesn't understand, you can't really understand from it everything, or at least so far we can. Okay, so in our work from last year, what we did is we gave a different construction, different way to get to that same modular form, or presumably the same one, via different exceptional theta correspondence. So 2.3. So this is our example. 24. So this is actually this theorem, but explained in some more detail. So what you do is you start with this character chi, and of course the theta series then is f, which is theta of chi, lives on PGL2. Note that I assume that it's trivial central character, and this is because I need to go to PGL2 here. And then the construction over there was to look at the work of Ginsburg, go to PGSP6, and then Gan-Gurevich, go from there to G2. So that was the previous construction. And now we go a different path to G2. We go to the unitary group in free variables, or a unitary group in free variables. So there's a classical sort of construction of how to go from here to here due to Howe and Kaminsky-Shapiro. And then we go from there to G2 using a different exceptional theta lift. So it's also an exceptional theta lift. But for smaller groups. So it turns out that the dual reductive pair, it turns out that PU free K and G2 form a dual reductive pair in a quasi-split group of type E6. So it's also kind of quasi-split according to the field K. So this is what we use in our work to construct something on G2. So let me state this theorem over here, but slightly more detailed. I don't know how I'm doing it. Hold on. Oh, okay, very well. Okay, theorem 1 again. Okay, let me. So this is this theorem. I just want to state it properly. So what we prove is basically we prove. So a short way to say it is that we prove the Arthur multiplicity formula for these a. So these a parameters, whatever that. I didn't write down any a parameters, but for this situation, we proved the Arthur multiplicity formula. So in particular, what we get is for each of these collections of epsilon p's, where epsilon p is in plus minus 1, epsilon p equals plus 1 for almost all p. Sorry, I should have said that before. And then also we need to assume two things. So we need to assume that epsilon p is always plus 1 if p splits in k, or if chi p squared is equal to 1. Okay, so we have to assume this. And then there's a global condition, which is that the product of all these finite signs should be minus the epsilon factor for chi cubed. So this is the global epsilon factor. And the minus is because I'm actually ignoring something at infinity. So that's what when you have this collection, you get, according to this collection, a quaternionic modular form, ff epsilon of weight k. Okay, and this is under the same assumption. So L, F, 1/2 is non-zero. So we need this for the non-vanishing of the fatal lift. Okay.
F is this theta he.
Sorry?
And F is this theta chi from chi coming
So
from.
this is defined as the fatal lift of some sort of modular form on PU3, so maybe.
I meant the initial F, the little f.
Oh yeah, sorry. Yeah. Yes, so F is already this modular form over here.
Can you?
Okay, so maybe I call this F chi epsilon in the other theorem. So but this is supposed to be, well, this would be like one of these guys for F, except these things are not fully determined, so we can't actually compare the two constructions. The point is that we get full control over what happens at the local places, and so this is also something that I should mention, that kind of what happens at the local places. So there's kind of the local input to this. So the local version of this result, which lets us control what happens at all the places, is and Marty, who's also here, so I wanted to mention. Cool. So I have little time left to talk about the second theorem. I think that's fine. So, the theorem is here. This is fantastic. But the first thing I want to state, before I actually say exactly what this theorem says, maybe I'll go over here, is that this theorem is actually a proof of a conjecture due to Dick Gross, and they are too fast. So what I want to talk about, maybe it's free, is Gross's conjecture, and then our result. So this conjecture was stated for formula of level 1. So conjecture, Gross, Eisen. So let's say L F 1/2 is non-zero, and F is level 1. So what Gross conjectured is that if sort of this cubic ring OE is equal to O straight E. So in other words, this is some sort of max. So this the cubic ring is kind of maximal. Okay, whatever that means. Then the Fourier coefficients of this modular form FF, let's say the Gangurevich one in this generality, since I'm not assuming dihedral, the squares of them should either be equal to delta E k minus 1/2 times this L value, F times E of 1/2, or, well, no, I didn't tell it, or 0 otherwise. Okay, this is not very helpful. So here I want to write if E is totally real. So that's so if E is totally real, you get this, and otherwise you get 0. And so actually he stated it kind of, if you look at the timing, it's actually before Gangurevich constructed these FFGG. Actually, he stated this more for like the conjectural forms that should come out of the Arthur multiplicity formula. He stated it even about this assumption, but then it becomes like a meta-conjecture assuming some other conjecture. So a concrete form that's not a meta-conjecture is to take those forms that were actually constructed and look at their Fourier coefficients. Okay, and then we prove this theorem. So sorry, I'm going from there to there because I guess it's already kind of written. Except I can tell you now more about this zero-ness of it. So we're familiar with all of this. And so what I should say is that this thing is either that or 0 otherwise. Okay. Ooh, this became an F. Okay. Okay, so this is 0. Definitely if E is not totally real. But then the other, so that's one condition, the same as in Gross's theorem. But basically now our form has level. So remember, F is theta chi, and it is some level n. These theta lifts will always have non-trivial level. And so for all primes dividing the level, I have to assume that the local sign that I chose to define my form at this prime is equal to some explicit local sign that depends on the cubic field and chi p. So I'm not going to actually spell this out, but this is an explicit local sign. So it really only depends on the local data of your field and the character. And this is what's needed. So actually this condition over here is also an epsilon condition. You could write epsilon infinity equals epsilon E infinity chi infinity or something. And so we need this condition at the primes dividing the level. It doesn't appear here because there F had level 1. Okay. So that's the theorem. Okay. Any questions about the statement? Yeah.
In the GG construction, do they also have the epsilon data?
Yeah, so it's not
a specific one, or
yeah, exactly. So they don't. Yeah, so it's somehow like it has to be there, but it's not because they never work out the full structure of the packet. They don't label all the representations. So, kind of this epsilon thing is you kind of construct a bunch of representations, and then you explain how you want to label them with pluses and minuses. You kind of want to label the local representations by these signs. So that's what happened in this local input, for example, is they explain how to label the local representations. And so here, that's not, in this setup, it's not all like carefully labeled. But maybe if you ask Wojtek Gan, he could tell you what's expected. And I think it's expected that you can construct almost the whole A packet this way, except for some like part of the A packet that will never come through this construction. It's a bit soft. It's somewhere there, but maybe already here it feeds into this construction. Yeah, it's a bit touch and go because not everything is worked out. Whereas here we get like the full Arthur multiplicity formula, so we get the full control over those absolutes.
Is the construction of Ginsburg also theta lifting, or?
Yeah, so this is interesting. I don't know so much about this, but actually it's something that's not quite a theta lift, but it involves looking at PGL2 times PGSP6 inside some bigger group, maybe GSP8 or something. That looks natural. But then instead of restricting the Weil representation, he restricts a slightly bigger representation than the Weil representation. So this has the flavor of like a theta lift, but it's also not a classical theta lift. It's something quite, I don't know, ingenious in some sense. It's not the obvious thing. Okay, so let me just, okay, where am I at? 1, 2, 3, 4, okay. Oh, so, okay, maybe I'll just, I was gonna talk about the proof, but maybe instead I should just give a few remarks and then finish. So, I wanted to, okay, so I'll just give a few remarks on this theorem. So, first of all, I wanted to say that, so remarks. So the first thing I wanted to say is that these are sort of the first cases of Gross's conjecture. So it wasn't known for any examples kind of fully. So this is the first time we have some evidence for this. But there is like related work, so most notably of Pollack, from the year maybe 22 is the preprint, and then Kim and Yamauchi from 24. And so they kind of study stuff to do with, well, Pollack studies these Fourier expansions on G2 in general and proves some very nice results about them. And in particular, in the level 1 case, for f equals to delta, he obtains kind of a proof of Gross's conjecture for not just for all e's, but when e is q times some f. So he doesn't get all the Fourier coefficients, but ones that are kind of degenerate, where one of the things is not, like a q splits off, so it's not a cubic field.
This delta is the usual delta.
Yeah, this is the weight, the Ramanujan delta function. So specifically for this example, he works out what's going on. And then Kim and Yamauchi assume that n is square free, and f is arbitrary. And they get the same kind of result, but they have to assume, kind of assuming the R for multiplicity formula when it's necessary. As I said, yeah, those cases of the R for multiplicity are not known, so they have to kind of assume that things behave as you think they behave, and then do something with that. I think when n is 1, so maybe this is, they show that this is kind of okay if n is 1. Or maybe, yeah, because then you just have to check something at infinity, which they check by hand, and you don't have the finite primes. And again, it's the same story. So this applies to both that and that. So they can get at these sort of Fourier coefficients. Okay, so that's the first remark. Oh, and for us, so I just want to say that this ends up being disjoint from our work. So for us, n is never square free, actually. So it's a bit subtle, but the conditions I put with the trivial central character together with this non-vanishing actually force a square in the level of the form. Okay, and then finally, so I want, okay, there's like several other things I could say. I guess I want to say that we have the same result for G2 over totally real fields. So in other words, like Hilbert, we can Hilbertify this Hilbert QL. So you can imagine what this result looks like. Okay, and maybe I'll finish here. Yeah.